list is a finite sequence of objects. Lists can be flat, like the first list shown here. Lists can also be nested within other lists, as in our second example. A linked list is a way of representing nested lists of variable length and depth. Each element is represented by a cell containing two items. The first is either an object or a nested list. The second item is either empty or is the remainder of the list. For example, the structure shown here is a linked list representation of the nested list above it. Our goal in this example is to formalize linked lists and define some useful relations on such structures. First step, as always, is representation. To talk about linked lists, we use the binary function constant cons, and we use the object constant nil to refer to the empty list. With this function constant, we can encode the list A, B, C, D, as shown here. Cons of A onto cons of B, onto cons of C, onto cons of D, onto the empty list nil. The signature for our language consists of some object constants, A, B, C, D, and nil, to denote the atomic elements, and a single constant binary function constant, cons. And we'll define three relation constants: member, among, and append. Let's start with the member relation, which holds of an object in a list if the object is a top-level element of the list. For example, B is the member of the list consisting of A, B, and C. Using the function constant cons, we can define the member relation as shown here. The first sentence states that an object is a member of a list if it's its first member. For all x and y, if x is a member of cons xy, member x is a member of cons xy. The second sentence states that an object is a member of a list if it's a member of the rest of the list. For all x, y, z, x is a member of z means that x is a member of cons of y and z. Now let's look at concatenation. The result of appending the lists A, B, and C, D would be A, B, C, D. Once again, our definition consists of two sentences. The first sentence says that appending an empty list to any list results in that list. The second sentence says that appending a list with X as the first element and Y as the remainder to a list Z results in the list with X as the first element, with the remainder being appended to Z. It's worth noting there's a similarity between this definition and the definition of plus in piano arithmetic. Here we have an identity nil instead of 0, and here we have cons instead of S. Otherwise, the definitions are very similar. We can also define relations that depend on the structure of the elements of a list. For example, the among relation is true of an object and a list if the object is the list itself, if it's a member of the list, if it's a member of a member, and so forth. In the example shown here, C is not a member of the list itself, supplied as the second argument, but it's among the list because it is a member of the second element of that list. The main lesson to be learned from this example is the use of binary functions in defining complex data structures. Also, lists are extremely versatile representational device, and it's good to become as familiar as possible with the techniques for writing definitions for functions and relations on lists. As is true of many tasks, practice is the best approach to gaining skill.